Okay, tonight we're going to talk about how to correlate data, and in particular the use of permeability equations. So it'll be equations that have porosity, permeability, saturations, things like that. We have one petrophysicist here, correct? Okay, so I can sit down and you can do the lecture, right? Okay, you'd like that? Okay. So the first equation that we'll talk about is Kármán-Kázzini equation. And the Kármán-Kázzini equation says that there's some unknown shape factor, and sorry if you use this a lot, I still don't know where they get that number. And then there's the formation factor, which we saw from Archie's. And then there's an R squared term, which is a ratio of pore volume to surface area, which is dimensionless. And then there's a conversion factor. I hope that's someone in here printing. Is it? Yeah. So what we're going to do is we're going to let it print, assuming it stops. And if they begin to walk in here, we're going to hit them with a book. So next is the Berg equation. We talked a little bit about the Berg equation. The power to that equation is 5.1. In the past, I would just pull the power out of the wall. So we'll give them a break this time. And it is based on the diameter squared. So again, permeability in millidarcies, porosity in fraction, and grain diameter in micrometers. And you'll notice this equation is only valid for porosity greater than 30. So that's pretty limiting. And I think the whole point of this was really that Berg, if you get a chance to read his paper or his book, I've included his book, I believe, as a reference in the course. If I haven't, I'll add it to that. But he does a really nice job of deriving these equations for permeability in terms of perfect packings of spheres. Sorry, I had to think about that for a second. And he wasn't the first one to do this. This work goes back to the 1920s. Some people did some work on perfect packing of spheres. I just thought that he did a nice job of combining it into equations for permeability. Mostly their work was for porosity. And then there's the Timor equation, and we talked a little bit about it. The Timor equation has two empirical constants, three if you include the constant for saturation. But the goal here would be to have a porosity log and a water saturation log, and then you would determine these three coefficients independently. Okay? And so that's permeability, porosity, irreducible wetting phase saturation, and then these empirical constants. And as I mentioned, I usually point this out that too could also be another constant. Okay, so I've had enough of this. Excuse me for a moment. Can you derive the Timor equation? Yes, no, or maybe? Take a guess. Can? Maybe? Okay. Anybody else? Can you get close? Don't you love how when people derive something and they start getting close, I call it throwing sandbags out of the balloon. They just say, well, I'm close. This doesn't matter. That doesn't matter. Whenever we derive the Brooks, Corey, Purcell, Berdeen, Naquin-Thap, and Evans equation for capillary pressure and permeability, this actually drops out of that. I mean, yes, there's a million assumptions in between, but you can sort of see where Timor, his equation comes out of that. Now, Timor, he came along in the late 1960s. Again, his goal was to estimate permeability from well logs. So what you would do, of course, is have core samples and have porosity and permeability data and also saturation data, fit it with an equation, and then use your log values, your log derived values for porosity and saturation to predict permeability. And again, why do we do this? So that we can put it in a simulator. So there we go. Okay, so Coates and Denew, it's often just referred to as a Coates equation. It's another one like the Timur equation. They have effective porosity squared, and then this crazy ratio function for irreducible saturation, and then another square, and I'm not really sure what this hundred's for, but maybe that's some sort of constant that came up. Once you start down this road of trying to relate porosity and saturation with permeability, you probably ought to just do it empirically. That would be my recommendation. Let me see if I can do this without ruining the board, but I would probably write it as a general equation that would be permeability A phi to the B and then SWI to the C. Sorry, have you guys ever used a smartboard? No? Yes? This one's out of calibration. Where you put the pen is about a centimeter away from where it writes. So we'll mention that to the computer guys as well. Okay, no problem. We'll just make it go away. Okay. And then, of course, we have the empirical model of ARPS. And then, as I mentioned before, we can actually get kind of close deriving it with the so-called Brooks, Corey, Burdine, Purcell, Nacornthap, and Evans relationship. And essentially what you do there is you just keep chopping terms until you get this. So there's 5 possible equations for relating permeability. How many more are there? Do you want to give us any guidance on that, Mr. Petrophysicist? Okay. Myers-Briggs? I thought that was a personality test. Thank you, Mr. Sarkar. No, there's something called a Myers-Briggs test, which tells what part of your brain you use. But you could invent any kind of equation here, right? Can you make a more complicated relationship between the parameters? Now, everyone refers back to the paper that Dr. Valco, Dr. Dattagupta, and one of Dr. Dattagupta's students and I worked on back in 1994. And I admit that the idea was theirs and the application, I guess, was mine. But they were looking at well logging data, and they were trying to correlate well logging data with the alternating conditional expectation algorithm. That algorithm does not produce a parametric equation. It produces statistics telling you how related things are. It will give you an output variable, okay, but not an equation. And I know you're all going, well, how the hell does it do that? Look, there's some mysteries in life that are just too, in seriousness. The way it works is it relates each value to the other value. So it's a multivariate correlation algorithm. In theory, it should give you the lowest R squared. But it does not give you an equation. It does not provide a predictor. It provides an interpolated value. The key to this, and if you look at this piece of software, is Dr. Valco figured out how to fit the transform functions with polynomials or with whatever you want. And then once you've done that, you can extrapolate. And that was his contribution to the work. So that's kind of clever. I mean, you could use a neural network as well, but this is a one-pass filter type thing. So I use this from time to time to check and see if data are correlated. What is this? A lot of words, but what does it mean? It means check and see if the data are correlated first. Before you go crazy and spend 3 days trying to program something in Excel or trying to program something in R. And I'm absolutely certain that R and SAS and whatever other software you try to run will have something like this alternating conditional expectations algorithm where it will tell you how related the data are. Okay, Cam, you're looking at me. I'm going to make eye contact with you. Let's say that we get out of this algorithm, this alternating conditional expectations algorithm, we get an error of 12%, average error over all the data points. Let's say we have 1,000 data points, and it could be 5 columns of data, and we're trying to predict, I don't know, permeability on a bunch of well log traces or something like that. And we get an output, and it says there's 12% error. You feel pretty good about 12%? Sorry? Yeah, it seems pretty good. Okay, no problem. But we don't have an equation. Then we use Dr. Valco's trick, and maybe it cost us a percent or two, and we end up with 14. Okay. Then I come along and I run one of these equations on the data set, and I get, I don't know, let's be generous and say 14 or 15% error. Okay. And then, who likes neural networks? Somebody? Raise your hand. Okay, you like neural network. You run it on a neural network. And it comes back and it gives 3% error. 3. So the algorithm says, what did I say, 12? And your fit gives you 14, my fit gives me 14, and his fit gives him 3. What's going on? Is it possible to overfit data? Of course. All you have to use is a trend line and overfit the data and put the wiggles in it, right? So is that what a neural network does? Not exactly, but sort of. You guys know Dr. McCain? You ever had Dr. McCain for a class? Mr. Bake, you've been here a while. No? You never had Dr. McCain for a class? You should never, ever underestimate old people. You sit here and you listen to us and you think they're stupid, they're old, they're not paying attention. Dr. McCain did exactly what I just told you. We wrote a paper in, I think it was 1998 or maybe 99 or 2000. Dr. Valco, Dr. McCain, myself, and another person. And Dr. Valco fitted the data with the algorithm and got 12% as an interpolation. And then he got something like 13 or 14%. I fitted it. I got 13 or 14%, whatever it was. And then the other gentleman got 3. Okay. And Dr. McCain said, "Good job, boys." And we were saying, well, what about this guy that got 3% error? He goes, "No problem." He said, "Here's the other half of the data set." And he said, "Now I want you to run your algorithm without any correction. You have to just simply give these data to your algorithm or to your equation and then predict the average absolute error." Okay? What did your equation get? 14%. What did my equation get? 14%. What did his get? Sorry? 35. And he was screaming. He said that was unfair, that the neural network didn't understand. And we were just like, okay, what part of this doesn't the neural network understand? And my point here is, I guess, that, try to use statistics to give you guidance on what you should or shouldn't be doing. Back when I was a little bit older than you, I ran across someone who eventually became a lawyer, actually, but they wrote a book on neural networks. And you need to listen to people who worked on something, and they'll always tell you the truth. They'll always tell you the limitations. And they said, I never forget, they said, it wasn't designed for most of the applications people are using it for. We knew what we wanted it to do. And the same thing happened with the guy who invented streamlined simulation. He told me one time, he said, what we sat down to do was to try to make a very fast algorithm to interpolate data. But what people are using it for is something completely different. And he admitted that there would be advances, but some things have specific limitations. Can you guys think of something else that we use that perhaps incorrectly? Anything you can think of? So I threw neural networks and streamlined simulation out there. Anything else? I mean, reservoir simulation too. One of the things that happened recently with the so-called big data thing is that people were saying that they could make predictions that were not physics-based. So you could just take the data, shove it all into an algorithm, and out comes an answer. Does that make you... I mean, you guys are completely different generation. You're going to have driverless cars. pilotless planes and everything else. This doesn't bother you? Man, I want a pilot who's been shot at, who's been divorced, who's probably alcoholic. I want somebody that's afraid of flying, I don't want a computer that goes, oh, it's raining. We'll turn back, or something like that. I want a human being. But that's me. Your generation will be different. You'll see things differently. Can you think of an application where, we have probably overused it? Well, this might be one. That's what I'm trying to tell you. That's a good segue. But whenever we get to the end of the course, that's when I want you to tell me Darcy's Law. Because at the end of the course, Darcy's Law is going to be the key to everything we derive. And kind of like when you go to the grocery store and you pull the can out at the bottom and the whole thing falls down, that's what I want you to be able to tell me, is whether or not it'll fall down. And the answer is it probably won't fall down, but we're not sure why just yet. Okay? So end of speech, but I just want to remind everybody that once you start working on a data set, rather than spending 3 or 4 days on it, run it through one of these filter algorithms and see if the data are related. How many of you are going to take a stat class? One. Did you guys take stat? No? Don't need it. You're mathematicians. Yeah, don't believe in statistics. Yeah, I like that. Anybody else? No? Maybe. You did take one? Which one? Oh, it was elsewhere. Okay. I make all of my guys take stat 604 and 608. What's the problem with taking one of those two? Well, taking one of those two. They don't leave any space for the engineers, so you have to take it online only or web only. Yeah. Is learning from the web easy? No. You got to be able to kind of have a conversation with people and get an idea of what they're thinking at the time. But I would recommend that, if you have to take an outside class, you do consider those. You don't want to be like me and be an armchair statistician. You know what armchair statistician is? Somebody that taught themselves. That's kind of a dangerous thing. Eric, you're back there smiling. You're afraid of people that taught themselves how to do things? Back when I was young, people didn't have to have a driver's license because they taught themselves. I mean, they did have to have a driver's license, but only if you got caught speeding or something. I mean, I knew people who never did have a driver's license. And why bother? Because they taught themselves. Of course, I can also tell you that I had a couple of 14-year-old friends who got in the car and immediately had accidents. But that's life, too. So today, we're going to look at this data that Dr. Berg generously provided me. Now, when you would go over to Dr. Berg's office, and it was almost half the size of this room, maybe. Also, after they banned smoking on campus, which was like 1985, Dr. Berg still smoked in his office. And it was like being in some sort of Moroccan, smokehouse or hookah house or something like that. He'd be saying, Dr. Berg, you're not supposed to be smoking. Yeah, I know. And he'd be standing underneath the no smoking sign, But you'd go see him and you say, Dr. Berg, I need a set of data because I want to do something like this for class. And he's short little guy, He walks over and looks at filing cabinet number 1, looks at filing cabinet number 2, and then he reaches in, just almost like magic, pulls out a folder. He goes, here, start to take it from me. Bring it back. And then so this is the Cotton Well in Burleson County, Texas. Do you guys know where Burleson County, Texas is? It is. But where does it start? About 10 miles west of here at the Brazos River. Okay. And so this is pretty shallow, actually. You could say, well, these are subsea depth, but I don't think what's our height above sea level here? About 300 feet? Yeah, so we probably won't flood anytime soon. So the core data, here's the permeability, here's the porosity. Man, this thing is really out of calibration. Holy cow. All right, we're going to pretend like we know what we're doing here. And so the core and log data is fairly well correlated. I'm trying to, God, this is ridiculous. All right. Sorry, everybody in distance learning land. I'll ask him to calibrate this. At any rate, we shall try to persevere. So the core data for the saturations is here. The log data for the SP, which is the spontaneous potential, and the log data for resistivity is given here. Now, Mr. Aldana, the first thing I want you to tell me is we shouldn't try to correlate this data, should we? Does it? Can you see it? Do you play chess?
Not really.
Nobody? Juan, do you play chess? You seem like a chess player. Anybody in here play chess? No? Sorry? Anybody else? Nobody. Everybody's like, don't raise your hand. Don't raise your hand. So I'm playing with my 5-year-old son, and I know nothing about chess, and I move the piece, and he's like, and I go this way. I go this way. So that's why I'm asking, do you play chess? Do you see what this is going to look like? The bottom zone, it's a waste of time to correlate it because it's flat. Okay? The permeability is basically constant. Does everyone see that? So the permeability here varies only slightly. The porosity varies only slightly. Would you say these are highly correlated? Yeah. This is going to be easy. Okay. Now, what about the top zone? It bounces around. Remember, each one of these lines is a factor of 10. So it's got almost a factor of 100 distance. There's a little bit of an issue with the lab and the neutron porosity. They're not quite correlated. They could be better. This is on a logarithmic scale. This is on a Cartesian scale. So I guess you could say it's okay-ish. And then the saturations, you know, they are what they are. And then the log data. So the resistivity data kind of goes this way. The SP data goes this way, and the resistivity data goes this way. The resistivity data doesn't really have a lot of character in the lower part, but it actually does have a lot of character in the upper part. Sorry, I keep getting these backwards. I need to be a geologist because geologists think from the bottom up. Sorry. Any rate, I think everybody understands. All right, so let's see what happens. So we're going to focus on this interval. If you look back, these depths are 2620 to 2680. So we're going to roughly look from 2620 to 2680, fit that, and then extrapolate it using the porosity, SP, and resistivity log. What do you think is going to happen? Is this story going to end well? Okay, so as I mentioned, the lower zone, there's really no need to try to correlate the permeability because it's basically constant. The upper zone does have some character, and we might be able to do something with that. Again, this is core porosity and core permeability. So both of these are direct measurements in the laboratory, and they should be reasonable. Okay. Now, I know, Mr. Aldana, you want us to draw a line, right? So there's a line, and you want us to draw another line, so there's a line. All right. Let's go to the next one. Okay, so now we're comparing core permeability and SP, that's spontaneous potential. Well, if it was constant before, it's constant for anything. It's kind of like well testing class, okay? So it's permeability is no matter there. What do you guys think of this? Is this a good line? Is it highly imaginative? Gabe? Miss Wang, Miss Zhang, you would do this, right? You would just put a big circle here, and you would go get this thing, and you'd make a gigantic question mark, and then you would turn all these things off. What happened to my question mark? There it is. And then you'd go find, see, I do know how to navigate in here. Not very well. Where's my, man, this drives me crazy. Why can't they just leave it up here? What's your favorite size? Like 72. Is that big enough? Is this what you would do as mathematicians? Do you see a trend? Do you want to throw a lifeline to the back of the room? Okay. Second row, does anybody see anything? Comedian? Should I call you Joker? You like that? Yeah. Or maybe Deuce might be more your. Yeah. Okay. Because the Joker, you can take that out of the deck, right? But you got to leave the 2 in. Anybody got any comments? All right, let's save the question mark. And let's use it here. So this is core permeability versus saturation. And as usual, permeability was constant, so it doesn't really matter here. But God only knows here. Now, if I pull this out of the way and I draw an ellipse, oh, you can't turn an ellipse in this program, can you? You can't rotate it. Can you? No, forget it. Sorry. But we might be able to. It's pretty silly that we can't do that, but at any rate, pretend this is an ellipse. It's called a shoebox ellipse. What about that? What should permeability go down with increasing saturation? Yes. Okay. And then this is core permeability versus resistivity. Now remember what you said before was that Archie, he hit the nail on the head, and there should be a relationship. There's no relationship there. Is there a relationship here? We need to go back and check and see which points these are. But yeah, there does appear to be a relationship there. Maybe. Okay. So then we run power law regression on each one of these. And this is pretty easy. We use the permeability is correlated with the log porosity, the log RT, and the log SP. And this is okay. I mean, you can argue whether you like it or not, but it's okay. And then what happened here? Mr. Aldana, any comments? Have you ever seen a politician speak? Like in person, a politician? No? Not really, no. You don't like politics, do you? You don't like anything except doing petrophysics. I can see that.
Oh, yeah.
What else?
Soccer.
I knew you were going to say that.
Why?
Yeah. I can see it in your eyes. Football. Yeah, I got it.
No, soccer.
Yeah. How old are you?
I'm 28.
28. So I had a student who was in his 30s. He was from Colombia. And he went and played with the younger than 30s. And he came in and he looked like he had been beaten and dragged behind a truck. And I said, "What happened to you?" And he said, "They were nice to me at first. And then they beat the living hell out of me." And, so when you're playing soccer with these guys, the friendly games on the other side of the parking lot, be careful. Stay within your age group. It's safer that way. That's true also for a lot of things. I'll just leave it at that. Okay. So politicians, they like to speak in threes because they can remember 3 things. Okay? You like that? All right, so I'm going to speak in threes. There's 3 possible things that's wrong with that lower trend. Anybody want to volunteer? Ricardo? Okay, the data could be wrong. Hadn't thought of that. Thank you. Anybody else? Camion? Gabe? Eric? Ooh. Everybody, when Eric leaves today, he gets a hug. Okay? Is it the wrong equation? Explain wrong. See, this is where you split. Wrong has two directions. Nah, you don't get a hug now. Actually, you get a swift kick in the out the door. Anybody else?
The coefficients could be wrong, but the structure may be.
The structure of the equation could be wrong. So instead of being a power law relationship, maybe it's something else. Power law is really flexible, right? It takes each parameter and it just weights it with a power. That may be right. It may not be right. But you're on the right track. So one possibility is we don't have the right structure of the equation. Correct? It could be the wrong form. Okay? What's another one? Ladies? No habla? Mr. Bake? It's along the same lines as structure. Anybody else? You're thinking that it doesn't represent one of those? What I'm thinking is it could be the wrong form of the equation. Or what else, Mr. Liu? It could be that the equation is not complex enough. That's not the right word. I'm not thinking about it correctly. But one thing, it may not be power law. And the other thing, it may be a more complicated relationship. You have very simple relationships between each parameter. Technically, they're just linear. If you take the logarithm of that equation, they're just linear. Is life linear? You know, and I don't know if Alex is going to talk about this, but when you look at computer algorithms when they started in the 50s, all computer algorithms boiled down to what, ladies? In the 1950s. You don't remember? What kind of calculations can computers make? Add, subtract, multiply, divide, and true false. That's it. Really and truly, that's all computers can do. Everything else is us. So what kind of equations have addition, subtraction, multiplication, division? Sorry? What's more than linear? Sorry? Polynomials. So is the universe polynomial? Of course not. We have all sorts of special mathematical functions. But how do computers see them? All computers can do is add, subtract, multiply. Who's got a calculator? Who's got a phone? When you make a calculation, what does it do? When you push cosine on your calculator, what does it do? Man, you guys are scaring me. You're the future of this discipline. Sorry? So there's an equation. And you just said there's either a power series or a Taylor series or something. But when you boil it all down, there's a really long equation that's a polynomial. Sorry? It's truncated, but fortunately with trigonometric series, you can only represent part of it and still get a really accurate answer. How accurate do these equations have to be? Cam? They have to be accurate to machine precision. So when you go back and you look at the work that was done in the 50s, 60s, and 70s, there were huge subroutines with numbers that go from here to here, trying to calculate the polynomial that represents that. Now, you can have polynomials within polynomials. You can have polynomials raised to powers, right? All of that's legitimate. It's going to get a little complicated, but all of that. By the way, how do you calculate a logarithm? There's got to be a polynomial for a logarithm. There's got to be a polynomial for an exponential. Okay, let's flip it the other way. How do you calculate something raised to a power?
Multiplication.
So you can multiply a number by something. If I say that I want to take x to the 1/2, how do you get that? Mr. Liu knows. You use logarithms because it's 1/2 multiplied by the logarithm that exponentiated. If you have an equation that is accurate to machine precision for logarithm, and you have an equation that's accurate to machine precision for exponential, poof, you're done. But they have to be that accurate. Sorry I went that direction, but I'm trying to make a point. What were our three things? We could have the wrong structure of an equation, and we could have the wrong complexity of the equation. And what else did we say? The data could be wrong. The data being wrong, generally speaking, doesn't light up like this. Okay? It does not go along that direction. But this is why running the data through R or SAS or ACE or something like that will tell you immediately there's a relationship. Okay? Now, having said that, what did I do on the right? By the way, you know these are two separate systems. These are two separate geological systems. And Mr. Aldana is going, you can't do this, you can't do this, because he knows exactly what I'm about to do. What did I do? I put both sets of data into one equation. Say it. Say it. You can't do this. But what happened when I did was that equation was more complex. And by making that equation more complex, you can see that there are cross terms. X, Y, and Z are the logarithm of resistivity, porosity, and SP. But when you start multiplying them by each other, you're getting cross terms. You're getting influence. Okay? This is not a great example, but it's a good example to explain this. What happens if you sent the whole data set to a covariance algorithm? I'll be honest, I don't know. But I can tell you, if you send the whole data set to the ACE or GRACE or whatever you want to call it, that alternating conditional expectations algorithm, it's going to show a stair step. One set will be represented by one part, the other set will be represented by the other. It knows there was a change. It knows there was a change. Again. Do you guys like problems like this? Not really? No? Honesty is appreciated. Okay, so here's our prediction. There's the data, and the line is the prediction. Mr. Mayol, what's your thesis again? Louder. Mass volumen, yeah, louder. Okay. That doesn't really count. I wanted you to say something like, I'm going to predict oil price. Okay. Anybody want to predict oil price? Cam? We had a student last semester who used fractals to predict oil price. And he painted the page black, and then he plotted the average function. What did the average function look like? And I'm just saying this for the sake of you. I'm not saying, there's the camera, I'm not saying it was wrong. I'm saying that just for the sake of discussion, if you took the historical oil price, fitted it with fractals, and predicted it, what do you think is going to happen? Sorry? That would have been preferable, thank you. No? What did it do? Sorry? It went straight up? Anybody else? Anybody else? Anybody else? Anybody else? Nobody? Mr. Petrophysicist? Went down? Why?
Because majority of the data historically is below 40.
I hadn't thought about that. Anybody going to take a guess? Mr. Liu? Chaos. So it did look sort of like a jump rope. You remember jump ropes? It had a couple of places where it was fixed, and then it bounced all over the place in between. Fractals. Fractals have a repeatable pattern, right? We pointed out during the defense that the forecast looked like a mirror image, like if you folded the piece of paper back that way, which is exactly what you would expect, I think. And the student, you could see, was imagining of all of us dead, you know. I mean, be very careful when you start forecasting. Be very, very careful. What's the purpose really and truly of running a forecast? I want you to think about this. I have to make a presentation in a couple of days on forecasting, and I hate these things. Why? Because I could give all of you the same piece of paper with the same data on it, and all of us would come up with a different forecast, and they would all be just as valid by some metrics, by some criteria. Why do we need forecasts in the oil and gas industry? Louder? Why? Why? What does it really boil down to? More specifically, whose money? The banks, right? Okay, the investors. So if you borrow money from the mafia, do they care whether or not the horse broke its leg or, you know, somebody cheated at cards? No, they want their money back. And the same thing is true here. So we adopt standards of practice where when you make a prediction, you have some guidelines on it. Why? Because if everybody makes a prediction the same way, then there's some basis for that. Okay, forget simple projections. Now, why do we do reservoir simulation? Oh, I'm sneaky. Sorry? Is that really what we want to know? Okay. Do you know that during the 70s and 80s, and actually even now, Exxon will not use a reservoir simulator for forecasting? They use it only for interpolation. So why do they do it? It's to calibrate their data, to understand what it means. It's to gain insight. Where do I drill the next well? How do I produce the next well? When can I expect liquid? When can I expect water? When can I expect to have to go on artificial lift? Those are the kinds of questions. They're not making a projection for reserves. You guys are too young to remember, but Shell got their hand slapped in 2002, 2003 for defining things as reserves that weren't reserves. They made an institutional error in a way. They had some assets in Nigeria, and I think it was assets in Australia that were not producing. By the rules of accounting, Gabe, if it's not producing, it cannot be defined as reserves, right? So what they did instead is they went on this draconian method of predicting forecast. You could only make a 2-year forecast. Yeah, they didn't care. They were going to have the most conservative forecast, period. Okay. What do you think about predicting permeability? If I were to give you a homework on this, which I don't think I will, what would your first step be? Are you free to consult?
No, I would check the quality of the
You check the quality. Okay, so you go back to the logs. You'd run it through a logging program or something and check where the maximum and minimum values are. But after you've done that and you're satisfied the data are accurate, then what would you do? And for these ladies who don't know anything, you've got curve number 1, curve number 2, curve number 3. And they're all related to curve number 4, but not exactly. Okay, so now you have to figure out a way to combine them. How are you going to do that?
I will correlate which one the best relation.
The best zone,
One.
or are you going to look at one-to-one correlations, or are you going to look at multivariate correlations? What are you going to do?
First, to get an idea of behavior
One-to-one. But one-to-one correlations usually are just indicators. Okay? All right. But the most important thing you said is you would quality check the data. Okay. And the rest is just some discussion from Nelson. And for the sake of argument, we can take a look at it. What Nelson tried to do was he tried to go back and look at every porosity permeability correlation that had ever been published. So it's a little bit complicated, but here's your scale. And millidarcy would have been low permeability. Microdarcy would have been very low permeability. Shales would be down here. This would be the Middle East. Actually, up here would be the Middle East. Well, no, I shouldn't say that. This would be the Middle East. And this would be like beach sand or that sort of thing. And so he's trying to show that there are different possible correlations there. Again, this is just possible correlations. He then shows data from different people. So you have a permeability porosity relationship. And of course, you can draw a line through it. And you can draw a line through it. Okay. Sort of like what we talked about before. Now it gets a little weird. Here he's got a correlation where he shows permeability and millidarcy versus porosity. He says here is the impact of grain size, sorting, clay, and cements. Okay? So this, basically, the direction he's looking at is if you have cement and clay, it's going to drive you in this direction. If you have coarsening, then things get better. If you have fining, they get worse. Okay. And then he's saying, okay, with sorting, the better the sorting is, well, the worse the sorting is, the more it rolls over. Okay. And then Berg came along, and this is the equation I was telling you about before. This is permeability, this is porosity, and this is grain size diameter. So technically, he should have plotted permeability divided by grain size diameter squared. That would have given you a straight line. That's why this has a curve to it. But he's just showing what that could look like based on grain size. So if you plotted your data on here, you could check and see where it lies, and maybe that could give you some idea about grain size, but I don't think that would be a very good task. Next is the work by Timor, and you can see that Timor's got this equation, or this line, this line, and then this line. And I know you guys can see that the bars on this are huge, but that's okay. I mean, the potential scatter is what I mean. And then what Timor did is he made a correlation, and that correlation is permeability and millidarcies, and then porosity raised to the 4.4 power divided by saturation squared, and that gave him this equation. And he's saying that, hey, I can use that equation, that's that solid line in the middle, or that heavy line in the middle, and I can predict permeability from well logs. We probably should have tested this equation for our data over here. What do you think would have happened if we would have tested that here? And I know we don't have saturation, we have resistivity, but we could have substituted that in as a proxy. I don't think it would have worked very well. In fact, I don't think it would have worked very well at all, but that's okay. And then this is an interesting plot because it's 1994. Here's permeability, here's porosity, and this is an empirical relationship for nuclear magnetic resonance devices. Okay, so what they've done is they've correlated the porosity and the permeability with one of the indicators that you get out of a nuclear magnetic resonance device, which is the T1, which is the spin time. Okay, and so in theory, you should be able to estimate permeability with that. But of course, the truth is this has to be calibrated. Those coefficients have to be calibrated for a given piece of rock. Okay? This is used now as well. Okay? I believe that's it. Yep. Okay, so just to go through, this is a homework problem I used to give. This is a data set from Gomez et al. And here's what you were talking about, Mr. Aldana, right? You would do these univariate comparisons, and then you try to figure out what they all look like, and then you put it together and get a correlation like that. So tonight was pretty easy. I managed to be late. Sorry about that. My dinner date did not share the urgency I did in getting back. When I pointed out that, we're being recorded and everything, he said that's why he didn't teach distance learning classes. So I pointed out that's really not his to say. But okay. Everybody feeling okay about this? If I gave a problem, you'd be okay with this? Directionally? Directionally, yeah. Okay. And what would the first thing you do? You would make those small plots like these. You'd plot z versus x, or maybe I should say whatever the variable is, in this case permeability versus x, y, and z independently. You would not expect particularly good correlations, but possibly. And then you would combine them for an analysis. What would you like to have a correlation for? Just let's take 1 minute and talk about that. Describe something that you would like to correlate. Do you know your computer is, the internet wire is not in it? Is that computer on? Works? I don't know, I'm looking, the wire's hanging out the bottom. Okay, no problem. Anybody want to correlate something? Cam? No? Anybody? What would you like to correlate for Vaca Muerta? Okay. Okay. Do you think that you could predict the 3-month cumulative production based on the completion? Would that be valuable? Maybe. You'd need more than just the completion. You'd want a reservoir variable, maybe something else. Do you think recovery is a function of choke? I'm speaking another language right now, sorry. Okay. What I'm getting at is sometimes things that you think may not matter do matter. But you have to have a consistent experiment, and I think that's what you were talking about, Yvonne, is that each individual data point has to be determined consistently. You're going to hear a lot from now on about design of experiments, and I have to laugh because what it really means is just do the same thing. Don't try to change 3 or 4 things in an experiment. Change one thing at a time. They're going to tell you that you can change 3 or 4 things at a time because the statistics will make up for it. How do you feel about that? I don't think it's a very good idea. It might be like trying to change a tire while your car is still moving. All right, we're going to meet 3 times this week with me. We'll meet tonight, tomorrow night, and Friday night, and you'll meet Wednesday night with Alex. I'll send an email with all this. And yes, we'll get you pizza every night. Can't promise a candy bucket, though. Yes, sir.
Just one thing, for example, in minus few correlations work very well for certain sets of data.
Why do they work well for some? Sometimes it's just the way God wants it. I'm joking, but the simple answer is if there's an underlying physics reason and you have enough data, you have enough inputs, you have enough independent variables, you're going to pick that up. I mean, it's a great question. It's not really my area. It's more like a hobby for me, but there are people that sell services on this, and what they're going to tell you is that their algorithm can pick up the relationship between the parameters if you have enough parameters or if you have enough variables. Where I want you to be really careful with this, and I did spend a lot of time looking at this 3 or 4 years ago, but there's a company that did something called topological analysis of data, and it was fantastic for predicting outliers. Like if you wanted to know who the best player in the NBA was, it could do that. If you wanted to know who was going to score the most goals in soccer, it could tell you that with pretty good accuracy. It's a company called Ayasti, A-Y-A. Oh, I'll send you guys. I'll put it in the thing, in the email that I send out. What they tried to do is try to get into oil and gas to process, big data problems. And it turns out that, and this is a great question actually, that right now everything that we look at in terms of data has to be tabular. We probably 90% of the data we look at now has to be tabular. We cannot tolerate nulls, not zeros, but missing data. And some of that's an issue. They predict that within 5 years, that 90% is going to go down to nothing, because they will just gather all of this data and somehow figure out where the nulls belong. Now, I'm going to tell you guys right now that Ayasti got out of trying to do oil and gas. It got out of trying to do some other things. Where do you have more data than you can possibly imagine? What fields? Sorry? I hadn't thought of that, but that's pretty good. Anybody else? Sports would also fall under that sort of category. There's a lot of data there too. Biology, you get a hug. Yeah, so medicine, mapping genes and chromosomes and other mapping viruses, things like that. So they really tilted their rudder towards the medical profession. What's the number one data gathering institution in the world right now? Sorry? Economics? Do you have a phone? When you dial that phone, who records the call? Sorry? Who does it belong to? Who's Big Brother? It's the NSA, the National Security Agency, right? And China has one too, right? Okay. 3 of them? Is that what you said? Okay. How do they process that data? Cam? Gabe? Eric? I'm talking all the lucky sperm cells. Okay, they're technically not supposed to analyze the content, right? They're not supposed to analyze what you said on your call. But when you watch TV shows, sometimes they do. Okay? But what are they doing? They're monitoring who you called, how long you spoke, where they were, those things. Okay? So that's where all of this big data is really going. It's going into either cybersecurity or encryption. And one is just about the same as the other. You're either trying to, figure out what somebody did or encrypt it. So, sure.
For example, so if a particular set of correlations work very well for a certain group of data, why do we want to universally find a correlation for
Okay, do we want a universal correlation or do we want understanding of the physics? So you caught me in a lie. Because when I say I want a universal correlation, what I really want is an understanding of the physics. I want to understand why Archie's equation looks like it does, why the geometric equation looks like it does. If you look at the thesis that I had a student write several years ago, we were basically binomial. We were either looking at one or the other. Either this equation's valid or this equation's valid. And as always, I cheated. How would you cheat, Cam? I used both of them, and I used the scaling factor between them. That's another way. And what you're saying is, Tom, all you're really doing is you're cheating. You're assuming this set of physics is right if this equation is valid. This set of physics is right if this equation is valid, and if it's not, then you're cheating. And that's probably true. But my goal was always to try to understand what the mechanism was underneath it. But we cannot represent everything. I used to have a slide where I talked about all the things that permeability was a function of, and you basically go off the page. There's just too many things. So you do have to truncate the problem. What's the biggest factor affecting permeability? Well, obviously porosity, but it's not the only factor, and it can be reversed or even negated by other factors. So again, you're wanting to know what the physics behind it is. Okay, last question, anybody? Yes, sir.
We want not complexity but simplicity, more simple equation. Even though we know it's wrong, we can use it because it's funny because of that.
Okay, but still, what I would do is I would pre-process it with one of these statistical algorithms to tell you if there's a relationship in the data. Now, if you're telling me what you want to do is use the equation that he determined for India and use it in Indonesia, I'd say that's directionally okay, but you need to talk to him because you really need to know the depositional environment, the secondary processes, and so forth. If you're looking at beach sand or unconsolidated systems, they're all going to correlate the same. Well, sorry, they will be more predictable. But if you're just asking me what's the simplest equation that people have been using, it's Timor's equation. And it's been used since the late 60s. And it's an accident, right? It's simple, it's straightforward. If aliens came to Earth, they would probably think that everything we do is power law because Timor's equation is power law. A whole bunch of stuff we do in reservoir engineering is power law. A whole bunch of stuff you do in production engineering is power law. A whole bunch of stuff you do in chemical engineering is power law. That's my point is that would be the simplicity. I think we've talked this to death. I don't think I'm going to give you a problem on this. So you can probably sleep well tonight. But if I did, I think you guys understand what you'd do. You'd pre-process that. You would do some sort of check like this.
And I will not forget about the geology.
Yeah.
Right?
Never, ever forget about the geology. Every single time I teach on well performance, go see the geologist. For one thing, they will like to see you. They're lonely people. Nobody ever talks to them. But go see the geologist and ask them what they think. It's kind of like if you really want to make your parents happy, ask them for their advice. They lived their whole lives. All they wanted was that moment to give you advice. It's the same with the geologists. Their whole lives, they've just lived for that moment where they want to give you advice. Okay, so I'll end with it's going to seem like a joke, but it's the truth. Everybody ready? Deep breath. How do you tell the difference between a good geologist and a bad one? Cam? Kate? Second row? Third row? Math ladies? Got nothing. Do you know any geologists? Never been around any. I don't care what culture it is. I don't care what age they are. I don't care how much money they have or how successful they were. My correlation on geologists is the good ones never shut up. They talk and talk and talk and talk. I have been at dinner with geologists where they spoke for 3 hours and I didn't get to eat. You know, I have been in Mexico. I've been in Indonesia. I've been in Iran. I've been in Russia. I've been, even in places like Mozambique, and they just never shut up. I mean, you need to have some time allocated. And if you listen, you will keep from making a mistake. They will. You remember the cartoon about when the geologist is happy? It's when there's no reservoir left. They've taken it all and analyzed every sand grain. So, do you remember that cartoon? Yeah. Okay. All right, everybody. We'll see you tomorrow night. Have a good night. Thanks for coming.